Hello, my name is Caleb King, and this presentation follows the contributions of the Italian school to modern axiomatic geometry. This follows the development of modern geometry from its early roots in the late 1800s to the more modern conception we have of the field as related by Hilbert and the German school. I'd like to start by asking a question. What is geometry all about? How is it different from other areas of mathematics? Is geometry an idealized representation of the real world? Is it our world, but idealized? Or is it the logical result of following basic axioms to their natural conclusions? These are two very different ways of looking at what geometry is all about. And the two different ways relate very closely to the two conceptions of geometry that we'll be talking about in this presentation, the pre-modern and the modern ideas of geometry. Let's start with geometry as an idealized representation. This is the kind of geometry that I think if you asked Descartes or Desargues or Leibniz about, they would find this version of geometry very, very compelling. Our world is messy. It has wavy lines. It has points that aren't really zero-dimensional. It has textures that are hard to represent. But as we move from the real world to sort of our idealized representation of it as a drawing, then as a more precise drawing with absolutely straight lines and absolutely pointal points. And then finally, as we move from those representations to a more abstract version of coordinates, once we are able to move into analytical geometry. As we go through that transition, we get a more and more perfect representation of what is essentially a real-world phenomenon of that box. Modern geometry is an entirely different sort of construction. Rather than being an idealized representation of the real world, the geometry of Pache and Hilbert, which we'll talk more about later, was a geometry built on axioms and theorems that were formed from those axioms, and the connection of those axioms and theorems to our real world that we inhabit with a space with three dimensions and ideas of points and lines that we can understand in a visual way. This was only of use as an analogy. It was only of use because we could make arguments with drawings based on those things, but were not in and of itself fundamental to the nature of geometry. By the time the Italian school was important in the mid to late 1800s, there were many geometries that had been identified, other than the fundamental Euclidean geometry from antiquity. And mathematicians knew about the dangers of, in particular, Euclid's fifth postulate, and how denying it or construing it differently could lead to different geometries. Now, one of the first geometers to focus his efforts in this direction was Riccardo de Paulus, who seems to have specifically avoided the fifth postulate by focusing on projective geometry. And one of the things that he was able to do was to give projective geometry a coordinate system by placing the line in the plane in a correspondence with rational numbers. And he was able to identify a lot of the problems that needed to be solved in order to make projective geometry its own real field and start to formalize things. Now, de Paulus was not exceptionally rigorous and incorporated many of his notions from real space into his geometry, most notably in the idea of movement, which brought in all sorts of assumptions about the space being continuous. And also he drew heavily on Klein's formulation of geometry. One of the shining stars of the Italian school has to be Giuseppe Piano. And this man, along with a contemporary of his, Segre, were two of the people who really kind of took this idea of formalizing geometry in entirely new directions. Now, Segre and Piano were students at the same time and competed fiercely with each other. They had all sorts of interpersonal conflicts. They both studied and taught at the University of Turin. So these two men were very involved with each other's lives. And Piano was sort of the systemizer to Segre's innovator. And he constantly criticized Segre for his lack of integrity and built foundational underpinnings to all the things that Segre was doing, sort of pie-in-the-sky thinking about. But he still recognized the innovations that were happening in the field of axiomatic geometry and was able to do this well before Hilbert, for sure, and actually several years before Fano, who we're going to get into later. But as I said, this man was much more comfortable restating earlier ideas than going out on his own and creating his own formulations, which is a shame because he's one of the most rigorous thinkers in this history. But he was very tied to previous ways of thinking and doing things. This is a quote from Piano, which shows he was still basically an empiricist, still basically thought of geometry as an idealized extension of our real world. He said, quote, "Each author is allowed to accept the experimental laws that more appeal to him, and he can also propose any hypotheses he likes. But if an author starts from hypotheses that are contrary to experience, or from hypotheses that cannot be verified by experience, nor their consequences, he will be able for sure to infer some wonderful theory that will lead others to cry, 'What gain if an author had applied his reasoning to practical hypotheses?'" Piano uses hypotheses instead of axioms or propositions, but you get the idea here that he looked at proposing geometries with axioms contrary to experience as wasted effort. And you can see in this his conventional thinking. Let's contrast Piano with his contemporary, who he had many disagreements with, Corrado Segre. Now, Segre worked in the field of algebraic geometry, and particularly with the connections it had to linear algebra. And this made him ideally placed to see geometry as something other than just points and lines. Because he had to regularly look at higher dimensional spaces, he was used to breaking the idea of points, lines, planes, and looking at merely their representations in dimensional space. Because he routinely looked outside of their traditional meanings of these ideas, he was able to make large leaps in the area of axiomatizing geometry. And it was unfortunate that Segre was not a methodical thinker, and he made many errors. So this was something that his contemporaries never tired of pointing out, and it is a shame that he was unable to match his vision with his mathematical ability, but he does deserve credit for the advancements he made in divorcing the ideas of geometry from their traditional visual meanings. Here is a quote from Segre. He said, quote, "The geometry of n-dimensional spaces has now found its place amongst the branches of mathematics, and even if we consider it, aside from the important applications to ordinary geometry, That is, even when the element or point of that space is not considered as a geometrical element, and not even, which amounts to the same thing as an analytical element made of values of invariable quantities, but as an element in itself whose intimate nature is left undetermined, it is impossible not to acknowledge the fact that it is a science in which all propositions are rigorous, since they are obtained with essentially mathematical reasoning. So here, Seger was really tying geometry to the rest of mathematics. He says we're using the same reasoning here, and even if the essential elements that we're talking about don't have the characteristics we normally ascribe to points, lines, planes, and that sort of thing, we can still do a lot with rigorous thinking about these elements, which, when you think about it, is a really fundamental difference in the way he looks at geometry as compared to Peano and other pre-modern geometrical thinkers. Where a lot of this comes together is in a student of Segre, someone who has studied under him and knows about his sort of interesting insights into the nature of geometry, but is a little bit more able to carry out the project of defining these ideas in a rigorous way. And this comes along in Gino Fano. Now, he's a student, and he gets his real start by following a hint that Seger leaves in an article where he says, hey, wouldn't it be great if we could follow these areas of research? And Fano does. As he moves along, he begins to focus on the independence of his postulates, his basic axioms, where he says each, the postulate N must be independent from all the previous ones, that you can't get to the places you can get with postulate N by just using all the ones up through N minus 1. So this is sort of essential to his method. Now, he is still not as rigorous as Peano, but he's able to make great leaps by working in this abstract way that he gets from his teacher. Here are Fano's postulates. I don't intend to read them out here, but by way of demonstrating Fano's method, I'd like to show how even if 1 and 2 are true, with a less conventional understanding of what a line is, then that doesn't necessarily imply postulate 3. So, for instance, Fano described a situation where a line is defined as chords of a circle. And here, any 2 points uniquely define a chord of a circle. That's true. So postulate 1 holds. And the line determined by any 2 points of a plane lies completely in said plane. If you look here, the plane is that shaded region. So the plane is a really weird shape. It's not a rectangle extending outward in all directions. It's just that shaded region. It's all the lines that connect that chord to that point outside the chord. So it's just that shaded region. But you can see that you could pick 2 points in that plane that, if you connected them, the line would not lie entirely in that plane. So you can see that postulates 1 and 2 can be upheld, while 3 doesn't necessarily follow. And Fano really liked this method because it showed that 3 was an independent postulate, that you absolutely needed it, because without it you could show that things were true, that that the new postulate would completely remove from consideration. So this is a really essential part of Fano's method. Now, these first 4 postulates are the basis of a lot of great projective geometry. From them, we can get harmonic groups, harmonic conjugates. We can get that harmonicity is preserved by projection, and that harmonic groups are related by a finite set of projections. A lot of the things that we've learned in our projective geometry course are the result of these first 4 axioms. And one interesting question that arises from these first 4 postulates is, if you take 3 points and find the harmonic conjugate of one of those points, is it always a distinct 4th point? Or could it be one of the originals? So if you have A, B, and C Does D always and everywhere have to be a distinct point from A, B, or C? It's an interesting question, and Fano could not resolve it by just looking at his first four postulates. Now, you can see here in maybe the most famous finite geometry, including 7 lines and 7 points, that if you take the harmonic conjugate of B, you can see that it's itself. You can kind of see the quadrangle up top made of blue and orange lines, with pink being the diagonal lines. And you can see that B is intersected twice. So you can see that the first 4 postulates are upheld, lines are uniquely determined, and so forth, but that in order to show that all harmonic conjugates are distinct from each other, you need a further postulate. Now, Fano went on to develop quite a few more of these finite geometries to show how each of his next postulates were needed in formulating his theories. From these examples, I think it's clear how Fano liked to work. First of all, he got rid totally of any objections based on the lack of connection to the real world. This is something he got from Segre and continued, and it's characteristic of the modern approach and completely foreign to geometry before this. And you can see this happened well before Hilbert and the publishing of his big work, Grundlagen. So he also just accepted that the object under study are undetermined. Lines and points, they had to follow certain behaviors and have certain logical relationships to each other, but there was no insistence on defining these terms. Instead, he chose to focus on the independence of each of these postulates, showing how each one was absolutely necessary to show certain things. And this allowed him to begin to search for minimal sets of axioms for geometry, which turned out to be the big project of geometry in the modern era. So with all of this going for the Italian school, why was it the German school that finally began the big project of reframing geometry from its classical roots into a more abstract version that we see today? Well, there are a lot of reasons for it. The authors of the paper that this presentation is based on reference a lot of them, including the fact that German was a more widely spoken language than Italian at the time. And so many of the papers that were written in the German school were more widely read. It could be that the individual writers, the mathematicians, were just happened to be less clear in the Italian school, which is certainly true. They made they had less clarity than their German contemporaries. But the real issues, according to the here, are that despite these advances that the Italians made, most of the strange geometries they discovered were used as counterexamples. Fano, for instance, did not discover these strange geometries like the one I illustrated earlier with lines being chords in order to propose a new geometry. His idea was to show that his first 2 postulates were insufficient to prove obviously true things that he knew about the plane. These things were a way to get to the real geometry, and to make it easier for geometers to understand and tackle problems that ultimately came from the real world, which is where geometry, according to them, did come from. They weren't able to make that final leap of disconnecting geometry entirely from the physical space that we all inhabit. Another contention that the authors make, which I found really interesting, was that most of the work that the Italian school did here was not done in a strictly academic sense. It was done to sort of clarify the basis of geometry in order for teachers to teach more clearly and better. Uh, this wasn't supposed to be taking geometry to new bizarre worlds. This was supposed to be taking the geometry that everyone considered a basic factor of mathematics and making its roots clear to teach and to understand. This was a pedagogical approach that they were taking. This was to improve the teaching of geometry, not a research area in its own right. So all those bizarre geometries only took geometry instead further away from what they would eventually have to do, which is instruct undergraduates in the basics of geometry. So uh, the German school was entirely research focused, and in the end, it was Hilbert and Pache and others um, who who developed these ideas into a rigorous and eventually minimal set of ideas to form geometries, and not the Italian school. But without their contributions, it's unlikely that the German school would have come so far so fast and uh, done it with quite the same style. So I think this is an interesting foray into a little bit of history, and I hope you've enjoyed it as well.